AP 120, Chapter 6, Accessory Structures, Thermoregulation and Injuries. So, accessory structures, we talked about those briefly already. Many of these are found embedded in the dermis. Uh, One example of an important accessory structure is sebaceous glands. Sebaceous glands are always associated with hair follicles. This means sebaceous glands are not found in thick skin. Sebaceous glands produce a oily substance called sebum that helps to waterproof and moisturize the hair and the skin. Here's a sebaceous gland from a slide microscopic view. And acne is a plugged sebaceous gland. If you have a black or white head, basically the sebaceous gland is just plugged a little bit, not necessarily a huge deal, or it might start to get a little swollen and inflamed, leading to the white head. Black head just got, well, dirt collecting in it. These can expand, have more fluid and other pus and other materials build up, leading to a pustule. It becomes somewhat of a dome shape. Then you get the much larger nodules. Nodules end up spreading out deeper into the dermis and along the hair follicle, which can lead to scarring. And then you can have the extremely large and painful cyst, where the body actually forms a connective tissue structure around the site of the infection within the acne to help sort of isolate it to prevent it from further spreading. And again, cysts can lead to scarring. So acne, plugged sebaceous glands. All right, then we have American glands. American glands are sweat glands. They have a long duct going to the surface. They are found in all skin, thick and thin, and they produce what we think of as sweat. American glands produce sweat, and sweat is 90% water. And sweat is, of course, produced to help cool us off. That's why we produce sweat. The water from the sweat evaporates and pulls heat away from the body. Also, we can sweat for emotional reasons, like you get really nervous, you're going to give a speech, and then your palms of your hands and soles of your feet get a little sweaty, as it were. All right, next up is apocrine gland. Apocrine gland falls under the category of sweat glands, but it doesn't actually produce what we think of as sweat. Apocrine glands are always associated with hair follicles, specifically the larger hairs found in the pubic and axillary regions after hair growth from puberty. So the pubic hair and armpit hair have apocrine glands. Now, apocrine glands are always associated with these hair follicles, and basically they are producing a thick secretion. And this thick secretion that's got lots of protein and lipids in it is then eaten by some bacteria, and those bacteria produce the odor associated with, say, armpits. So that unpleasant odor is from bacteria eating the secretions from apocrine glands. Weird. So why do we have these glands? Well, it's thought that because they can become active when we're sexually aroused, that perhaps they are helping to produce or distribute things like sex pheromones. Now, we've never actually found any human pheromones, but there is evidence to suggest they exist. So apocrine glands might be associated with that. All right, some other glands. There are the ceruminous glands. Ceruminous glands are found in the ear canal, and they secrete earwax. Then, of course, mammary glands. Mammary glands are modified sweat glands. They, of course, produce the very nourishing milk for a newborn. All right, hair. Hair is found all over the body, except where there's thick skin, so not in the palms of the hands or soles of the feet, not on the lips or nipples or parts of the external genitalia. But most everywhere else, there's going to be at least a little bit of hair. Hair color is determined by genetics or hair supplies bought at a store. And when it's done by genetics, it is caused by the action of melanocytes. That's right, the exact same kind of pigment cells that give our skin its pigment also provides the color for our hair. The portion of the hair that sticks out from the skin is called the hair shaft. The portion going into the skin is the hair root, and then the structure that goes around the hair root is called the hair follicle. There's the lovely hair follicle surrounding the hair root. All right, it turns out that that the hairs have a epithelial stem cells at their base, so at the bottom of the hair root, and it's the cells on that single layer at the bottom that divide to produce new cells, and the new cells get pushed up, and then the cells above them get pushed up, and so on and so on. And so hairs are basically growing from the very base of the hair root. And this is very much like the epidermis. And just like the epidermis, these cells keratinize and die as they progress further and further away from the base. So hair cells are very similar to epidermal cells. And then, of course, there's lots of blood capillaries near the base of the hair root to provide nutrients for those growing, dividing cells. And here's just a slide of a hair. Here's where the dividing region would be. Here's the hair follicle going around the outside. Here's the hair root in the middle. Nails. Nails are protective coverings at the ends of our digits. And surprise, surprise, they are produced by keratinocytes. Again, cells that are similar to the cells in the epidermis. That are slightly structurally different. So there are cells that divide at the base of the nail, and then they push the new cell forward, which pushes the next cell forward, which pushes the next cell forward, and onward and onward. So it is at the base of the nail that the growth of the nail is occurring. And of course, the cells become keratinized and die as they are moving along the length of the nail. Also, the light color little crescent that you can see underneath your fingernail, that is known as the lunula. All right, moving on to thermoregulation, or regulating the body temperature. So we are always losing heat to our environment. There's always some heat loss through the skin. It is impossible to prevent that, except going into an environment that is much hotter than body temperature. But we do have insulation to try to limit the amount of heat lost. Is it from areolar tissue, adipose tissue, dense connective tissue, or stratified squamous tissue? It is adipose tissue, especially in the subcutaneous layer. All right, well, how do we respond if our body gets too hot? Temperature is too high. Well, there is one thing that happens is dilation of dermal blood vessels. So the blood vessels in the dermis will dilate, will get wider. That'll increase blood flow to the skin, and that will then carry more heat to the surface of the skin that then can be lost through the skin. To aid in this process, we will also sweat. Sweat, again, mostly water. The water evaporates, and that evaporation carries body heat away from the skin. And so that's how we deal with getting too hot. When we get too cold, our body also has mechanisms to try to prevent heat loss. To start with, we have the dermal blood vessels constricting. So these blood vessels in the dermis, they constrict, they get narrower, less blood arrives in the skin, so less heat is lost. Still gonna lose some. Skin needs some blood to survive, but it'll be less. Obviously, the sweat glands are inactive, and also unassociated with the skin, but it happens, is shivering. Muscles will contract rapidly, generating heat to warm the body up. And basically, these processes are actions to try to return us to the set point, to the ideal body temperature of 37 degrees. Good old negative feedback. Temperature of your body gets too high, then you sweat and dermal blood vessels dilate. Try to get you back to normal body temperature. Body temperature gets too low, then the sweat glands are turned off and the dermal blood vessels will constrict, decreasing blood flow to the skin and muscular shivering. Hopefully this will then raise the blood temperature, body temperature back to the set point of 37 degrees, and so on and so forth. All right, sometimes we get into conditions where we can't control body temperature. And those extreme situations are very dangerous. One example is hypothermia, low. Hypothermia, low body temperature, when your core body temperature is below 95 degrees Fahrenheit. Say when you get into an extremely cold environment, dive into a freezing lake, take a long walk in, say, 50-degree weather while it's drizzling and you're not wearing a waterproof jacket. Those can lead to hypothermia. Hyperthermia is when your core body temperature gets over 106 degrees Fahrenheit. When that gets that hot, you can start having your organs shut down. So basically, you want to avoid situations where the temperature around you is way too high and you have no way of cooling off. Unfortunately, there are now places in the world where, because of global warming, people certain times of the year cannot survive unless they're indoors, probably in air conditioning. Wound healing. Well, as we know, sometimes we get cut, and that's unfortunate. And if the injury goes down into the dermis, then the wound will lead to bleeding. So why must the dermal blood vessels be damaged in order for there to be bleeding? Well, it's because the dermis is the most superficial layer with blood vessels. Epidermis, no blood vessels. You can cut your epidermis, no bleeding. Dermis has blood vessels. If you injure the dermis, you get some kind of bleeding. And as a consequence, of course, blood cells, white blood cells, will come in at an injured site to try to keep an eye out for pathogens that might be coming in to destroy them. So the first thing that happens after an injury that leads to bleeding is the dermal blood vessels will initially constrict to reduce blood flow to the site. Makes sense, losing blood, don't want to lose too much. Then after that, inflammation develops. Inflammation, which leads to redness, increased temperature in that area, swelling, and pain. Pain to remind you you're hurt. Inflammation actually means more blood is flowing to the area, causing the redness, bringing the heat, causing the swelling. And that is important because that brings the white blood cells. Then over time, the blood will clot so that there's no more outflow of blood. And fibroblasts and other macrophages will arrive to clean up the injured site, get rid of any pathogens. Fibroblasts will start building new tissue, producing the collagen and the other extra cellular material needed. And then blood vessels get repaired and will start growing back into the area. And the new tissue, before it's completely developed, is called granulation tissue, before it returns to complete epidermal and dermal tissue. And then the scab forms. It's basically the leftover blood clot. And ideally, just the injury site will return to what it was like before and be nice and healthy and wonderful. But sometimes, if the injury is too deep, you get a scar, also known as fibrosis. Basically, there's an overproduction of collagen fibers, trying to compensate for the severity of the injury. And scars are never as good as the original skin tissues. Burns. Sometimes we get burned. First-degree burns mean we damage the epidermis and only the epidermis. Sunburn is this kind of burn. Touching something hot briefly can lead to a first-degree burn. It's sore, it's reddish in color, and it's often a little warmer. Second-degree burns. Second-degree burns burn through the epidermis and into the dermis. This causes, again, redness, pain, swelling, and often a blister forms. A blister is when the epidermis separates from the dermis and then fluid fills between the two structures. So a blister, epidermis separates from the dermis and fills with fluid. And then a third-degree burn is a burn that goes through the epidermis, through the dermis, and into the subcutaneous layer. So through the epidermis to the dermis into the subcutaneous layer can lead to redness, pain, blistering, and even charring. And third-degree burns are very serious. They can lead to nerve damage. So anytime you think you have a third-degree burn, you should get it checked out by a medical professional. And that is it for Chapter 6.